So how do we use this equation mathematically? Well, in the next section, we're going to talk about what this index of refraction is, but this is related to the velocities of the material. And this is Snell's law, is how we're going to do these mathematics practically. So Snell's law states that the index of refraction, so how much slower or faster the speed of light is in the material times the sine of the angle is equal for no matter what materials you go into. So here our incident angle is 30 degrees and our refracted angle is theta 2. So now we're going to practice doing the mathematics. We know the index of refraction for air is 1 and 1.33 for water. And when you use this formula, it doesn't really matter in Snell's law which you call 1 and which you call 2. We usually call the incident material 1 and the refracted material 2, but it's the same on both sides. So as long as you keep these matched up, it's not super critical which one you use where. So N1 is 1, and we want to solve for theta 1 here. That as we're a diver that looks under the ocean and we're looking at the sunset, and so what angle is the sun actually at if we observe it at an angle of 42 degrees. So sine of theta 1 is equal to n2 over n1 times sine of theta 2. So theta 1 is the inverse sine of that ratio. And now we can put our numbers in. Theta 1 is equal to the inverse sine of N2 with 1.33 over N1 of air times the sine of 42 degrees gives us an angle of 63.1 degrees. And we would expect that this angle with the lower index of refraction would be bigger. And here's the solution nicely typed up. We're going to look at another example of, here we have a glass cable that has a outside coating on it, and then it goes into air. So we're going to assume that this outside coating is transparent, otherwise the light ray would not go through it. So then we need to apply Snell's law, and what we want to figure out is what theta 2 is, measured not from the normal, which would be here, but measured from there. So we need to use for Snell's law the complement of theta 2, and here we also know theta 1, and we want to really know the normal direction, so we're going to use 90 minus theta 1. So we got to deal with this intermediate material, so the actual equation we're going to use is n1 times sine of 90 minus theta 1, based on how the angles are defined here, is equal to n3. You'll see why in a minute. We'll call that n3 times the sine of theta 3, and theta 3 is measured correctly. And then for going into the third material, we have n3 sine of theta 3 is equal to n2 times the sine of 90 minus theta 2, again measuring from the normal. And we can set these two equations equal to each other because we want to solve for theta 2, and we know n1 and theta 1. So that means these two basically cancel out. We'll set these two equations equal to each other. N1 sine of 90 minus theta 1 is equal to n2 times the sine of 90 minus theta 2. And now the rest of the problem is just algebra as we solve for theta 2 given all the other values. So here's that nicely written out, and then here's the algebra to take that equation that we just found. And you can see now why we had n3 is it gets eliminated from the problem, and we can simply start with theta 1 and theta 2, and we get that theta 2 is equal to 23.3 degrees. And this is common. You can do this. If there's an intermediate material that's pretty thin, especially, you can ignore it. The only time we couldn't ignore it is if we're looking at how much where the light ray will exit. We need to know how far it goes across that thin layer.